Now imagine that we were solving three separate auxiliary equations, and these were their roots. We'll be taking a look at how to get the equation for the general solution for each of these, starting with this. You can see that the first root is -4, which is a real number, but the other two roots are the complex conjugate pairs. So the equation for the general solution is going to be this. Now, the value of m1 is going to be -4, which is going to be written here. And this was the equation for the general solution for the third case, the case where we get the conjugate complex pairs. This alpha is a real number, and this beta is also a real number, but of an imaginary part. Now take a look at this question. Here we are having three conjugate complex roots. This means that we are having 6 roots in total. Hence, there are going to be 6 constant coefficients for each of these roots. We know that this is the third case, and the equation for its general solution is this. For 3 conjugate complex roots, we are going to be modifying our equation and write our general solution like this. You can notice that we were having 6 roots in total and 3 conjugate complex roots. So there are 6 arbitrary constants in this general solution. Now consider the case where we have repeated complex conjugate roots. Here, we are having 3 conjugate complex roots. This is the combination of the second and the third case. The second case deals with the repeated roots, and the third case deals with the complex conjugate roots. You can see that all 3 of these conjugate complex roots are same. So in this scenario, you'll be manipulating your general solution in such a way that it satisfies both conditions for the repetition and for the complex conjugates. The general solution is going to look like this. E power 2x is real part of the complex conjugate root, which is being repeated. So we can take this and factor it out. And cos and sine are appearing because of the imaginary part of the root. The multiplication by x and x squared accounts for the repetition of the roots. So this complete expression represents a general solution that takes care of both the repeated and the complex nature of the roots.